Hello everyone and welcome to the course Physics 103, General Physics 1. So today we'll study about the chapter 1 and in this chapter we'll study about all the units, the dimensions and dimension analysis of various quantities in physics. So firstly the introduction about physics. So before 1900 the physics was called as the classical physics, and after 1900 physics is known as the modern physics. In this course, we'll study basically the mechanics part of physics, and mechanics deals with motion of physical bodies using the Newton's equations. So whenever any object is moving, that study of physics is basically known as mechanics. So in this whole course 103 in Physics 1, basically we'll study mostly about all the mechanics topics. So these equations give us accurate results provided that the bodies in the question are macroscopic in nature. Macroscopic means which we can generally see with the naked eye. For example, all these objects like car, mouse, or fly, like this. So whenever the bodies, they are macroscopic in nature, and one more thing, that they do not move very fast. Very fast, how fast? Like the speed of light. The speed of light, which is 3 times 10 to the power 8 meter per second. So in mechanics, we'll study with the motion of physical bodies using the Newton equations, and we for these equations we just need to check these two conditions also, that the objects, they should be macroscopic in nature and they should not move very fast. So like if we have any microscopic objects and they are moving, we cannot study those objects under this mechanics. So measurement and units. So why we need the measurement and units in our general life? So anyone, all the people, if they use different units for the measurements, then like in the whole world we cannot check about the certainty or the accuracy of the measurements. So what we do, we have the international system SI unit of measurements that we use throughout the world for all the measurements of the quantities. So for the measurement and units, we use this SI system of measurements, and in this SI system of measurements we have base units and we have derived units. When we say base units means what scientists did, they specified some base units in physics and then they derived further units using these base units. Okay, so base units we have length, mass, so length, mass and time. So length, mass and time, they took these three quantities as the base units and then they derived all the other derived units using these three base units. So for example, if I say area, so area is what? Area is L square, right? So we derived the unit for the area using this length unit. So area is then derived unit. Similarly, your volume is L cube. So again, volume is the derived unit. So reporting values from measurements for the accuracy and the total precision of the quantities. And we also use some prefixes with these units, and we'll study about those also in this chapter. Mass. When we talk about mass, the relationship between mass and weight. So if you just think about these two terms, the mass and weight, what's the similarity between these two and what is the difference between these two? So when I say mass, mass means just the m. But when I'm saying weight, weight means m times g. So whenever you multiply mass of a quantity with the gravity of the earth, then that becomes a force, which is weight. The force with which earth attracts all the objects towards it. So that's the weight. So that's the difference between mass and weight of any quantity. Standards of length, mass, and time. For example, I step on weighing scale and it reads 120. Now 120 what? 120 lb, 120 kilograms, 120 grams, 120 what? So for each measurement, we need some units. So unless or until you specify, you give unit to a number, it doesn't make any sense. Okay, so just a number is nothing unless or until you give a unit to that number. So we need only to define few units for the following four parameters. So generally length, mass, and time. And sometimes we use electric current as well. But generally we use these three units as our base unit, the length, mass, and time. So standards of length, mass, and time. So these are the parameters, these are the quantities, length, mass, time, and electric current. Now, the units. Okay, so there is a difference between unit, symbol, and dimension. Okay, so right now we are checking about the units. So length, how we measure the length? We measure the length in meters, which has a symbol small m. Mass in kilograms with the symbol kilogram, kg. Time in seconds with the symbol small s. And we measure the electric current in amperes with the symbol capital A. So these parameters, these are the base units that we use, and then we derive all the other further units using these base units. So these are the SI system that is used throughout the world in the sciences. Okay, so scientists, they use these four parameters as their base units, and then they derived all other units using these four. Now, how do these map to the units which are commonly used in US? So 1 meter equals to 39.377 inch, 3.281 feet. 1 kilograms is 2.2046 pounds, means lbs, 35.274 ounces. So if you see like 1 meter, inches, feet, how these three different units, they are related to each other. Okay, so whatever the unit you are measuring, you are taking, you just need to know the conversion factor between the units. Then in physics, in science, we also use SI prefixes with the number. So how larger the number is or how smaller the number is, you're just gonna use these prefixes with the number. So in physics, suppose if you have any number, for example, 6 times 10 to the power 15 zeros, right? 10 to the power 15 means you have these 15 number of zeros. So So you're not going to write all the time that number multiply by this number of zeros. What you do, whatever the number you have, multiply that number by 10 raised to the power 15. This factor. So we use this factor, 10 raised to the power 15 with the number. And this factor is known as peta. So you can also write down that 5 peta seconds. Okay, so instead of writing 5 into 10 raised to the power 15 seconds, you can also say that this is 5 petaseconds. Okay, now suppose if you have anything 9 kilograms. Okay, so 9 kilograms. So you don't need to write 9 into 10 raised to the power 3 grams, because 10 raised to the power 3 is itself is kilo. Okay, so 9 kilogram means 9 into 10 raised to the power 3 grams. So this kilo is basically the Greek prefix, and we use this for 10 raised to the power 3 factor. And similarly, we have all these prefixes. So decimeter means 10 raised to the power negative 1 meter. So whenever you have like any number, so suppose 4 decimeter. 4 decimeter means 4 into 10 raised to the power negative 1 meter. So like this. So you have centimeter, millimeter, micrometer, nanometer, pico, femto, atto, like this. So in physics, and if you're gonna do higher studies in physics or sciences and all these things, you will generally see these prefixes with the numbers, that nanometer. So nanometer means 10 raised to the power minus 9 meter. Micro means 10 raised to the power negative 6, like this. So these are the prefixes that we generally use with the numbers in science. Now, the derived quantity, units, and the symbols. So see, I told you that we have base units, and our base units are length, mass, and time. So when we are saying we derive the units by using these base units, so suppose you need to find area, right? So area, symbol A, and what is the formula to find the area? That is width into length, right? And we measure the width in meters, length in meters. So your formula, your symbol will be, unit will be meter square, right? But dimension will be L square. We'll check about these dimensions also. Volume. Volume means width into length into height. You measure width into meters, length into meters, height into meter. So your unit will be meter cube. Now, velocity. So your velocity is displacement divided by time. So displacement, since displacement is measured in meters, that is basically a distance, and time we measure in seconds, so the unit for the velocity will be meter divided by second. And similarly, you can check all these units for all these derived quantities: force, pressure, work, power, and like this. So that we did about the units of the quantities. Now we have dimensional analysis. So dimensions basically denotes the physical nature of a quantity. Always do a dimension analysis whenever you are solving any problem in physics. So we have these base quantities: length, mass, and time. And as I told you, the dimension for these quantities is L for the length, M for the mass, and T for the time. Length, mass, time, they have units: meter, kilogram, and seconds. Okay, so make sure, don't make this mistake. Mostly students do this. So unit for these quantities is meter, kilogram, and seconds, and the dimensions are L, M, and T. So there is a difference between unit between this unit and the dimensions. That's the difference between these two. So all the measurements in mechanics can be ultimately reduced to the measurement of length, mass, and time, because these are the primary dimensions, and we are deriving all other units, all other quantities by using these primary units, these primary dimensions of the base quantity. So for example, how do we derive the dimension of a parameter? So suppose we use an equation that involves the particular parameter we are interested for. For example, you have this equation v is equals to x over t. V is equals to x over t means your velocity equals to displacement over time. So in every equation, you need to check that your left hand side is equals to your right hand side. So if you check in this equation, v is equals to x over t, your v is what? L over t, right? The displacement divided by time. And on this right hand side, you already have x, which is L basically, and t is this capital T. So if you check on both the sides, you have L over t and L over t on right hand side also. So that means this equation is dimensionally correct. So dimensional analysis, the dimensions of a parameter such as velocity does not depend on the units. V is L over t by L over t. V is expressed in meter per second, centimeter per second, or miles per hour. So this means that dimension of any parameter does not depend on the units. It just depends on the dimensions. You whether measure your quantity in any of these units, meter, centimeter, miles, or whatever, but you'll just check the dimensions for this. So dimensional analysis can be used to detect errors in the equation also. Now let's check this equation. So for example, you have h is equals to half of g t square. Now again, when you're doing the dimension analysis, you just need to check whether your left hand side is equals to your right hand side. If you check in this equation, your left hand side is h. H means just the height. So we are going to measure the height in length dimension, right? In dimension of L. And on the right hand side, you have half of gt square. And now remember, whenever we are doing the dimensional analysis, we don't consider the numbers in the equation. We just check the parameters. So we are left with gt square. So gt square. Now g is what? G is basically your acceleration, right? So acceleration, if you check, acceleration is again the velocity. Acceleration is your velocity over time, right? So velocity is again your velocity is displacement over time. Okay, so acceleration is velocity over time, velocity is displacement over time. So if you check this acceleration, if you check, plug in this dimension for this acceleration, so here for velocity you have lt minus 1. So if you plug in this number in this equation, you will again get acceleration will be lt minus 1 divided by t. That means the acceleration has the dimension of lt minus 2. Okay, so your acceleration, this gravity is lt minus 2, and here you have t square, that is t raised to the power 2. So you're going to cancel this t square, t raised to power minus 2 with this t square, and you are just left with L on this right hand side. So on left hand side you have L, on right hand side you have L. That means your equation is true. So this is true for this equation. Now if an equation is found to be dimensionally incorrect, then it is incorrect. But if an equation is dimensionally correct, it does not necessarily means that the equation is correct. Okay, so you just need to check like whether this is dimensionally correct or dimensionally incorrect. So now let's try this incorrect equation, because when we are checking the dimensions, we don't take into account the numbers with the equation. So for example, when you are checking this equation, h is equals to 1 by 3 times gt square. So again, left hand side you have height, that is L. On right hand side you have 1 by 3 gt square. So since you are dropping this 1 by 3 for the dimension analysis, so you will again get L on the other hand side. So although you are getting same left hand side is equals to right hand side, but this equation is actually incorrect. Okay, so whether this is dimensionally correct, it doesn't mean that it is actually correct. Okay, so that is the dimension analysis. So now dimension is what? It is useful to consider the physical dimension because it provides a way to track the symbols mean through the long calculations. So a process is known as dimensional analysis to get that. So dimensions and unit of these quantities. So suppose you have area, you have volume, speed, and acceleration. Okay, so now you can see the difference between the dimensions and the unit. So when we are talking about units, for example, so unit for the area means meter square, for volume meter cube, for speed meter per second, for acceleration meter per second square. Okay, and when we're talking about the dimensions, so dimension means for the area you have L square, for volume you have L cube, and for speed you have L over T, that is displacement over time, and for acceleration you have L divided by T square, because acceleration is again your acceleration is your velocity over time, and then your velocity is displacement over time, and like this. So you can find the dimensions and units by using your base units. So this is a table or all the examples for your units, for all your units and dimensions. So guys, for this whole course, even like these are just the simple formulas, and you should know these formulas for this course, even for the physics or in science. For all these things you should know, like length we measure in meter, it will have the dimension L. Time we measure in second, mass we measure in kilograms, area has the formula meter square, volume meter cube, density is mass over volume, so you're going to measure mass in kilogram, volume in meter cube, so it will have density. So density will have units kilogram per meter cube, and its dimensions will be n divided by L raised to the power 3. Okay, and these are some more quantities with the units and the dimensions. Just try to do all these definitions, check these formulas, and in formulas put your units, put your dimensions, just check these all the dimensions for all these given quantities, and this is really good. This will be really good for your practice for this course. Okay, analysis of equation. So this is what we did actually, right? So velocity is what? Velocity is your displacement over time. This is the formula for the velocity, and these are the dimensions. So when you're checking again the left hand side, your right hand side, you will get, so this equation v is equals to at is dimensionally correct because we have the same dimensions on both the sides. But if you will get this equation, v is equals to a with the t square, then that would be dimensionally incorrect, right? Because for velocity you will have L over t, for acceleration you will have L over t minus 2, and here you will have t, so you're going to cut this with this. So on this left hand side you have L over t, on right hand side you just have L. So this equation is dimensionally incorrect. Okay, now analysis of a power. Analysis of a power. So suppose we are told that acceleration of a particle moving with uniform speed v in a circle of radius r is proportional to some power of r, say r raised to the power n, and some power of v, say v raised to the power m. So you need to find the values for the n and m and write the simplest form of an equation for the acceleration. So write an equation for the acceleration with a dimensionless constant of proportionality k. So just take any constant and write down the variables with the powers. So they are saying that the acceleration is proportional to r raised to the power n and v raised to the power m. So what we will do after that, just substitute the dimensions. So for acceleration, we know the dimension is L over t raised to the power 2 because this is velocity over time, right? So with this, on right hand side, you have r raised to the power n. Now r, again we are going to measure r in length, so means the L raised to the power n. Then for velocity we have L over t, so we are going to plug in for velocity L over t raised to the power m. Okay, now if you check on right hand side, for you have power of L as m and n, right? So you have L raised to power m and L raised to power n. So both will add up. So you will have L raised to the power m plus n. And at the bottom you have only t, and t will have the power m only then, right? So now what we can do, we will just equate the powers of the same quantities on both the sides. So L length has n plus 1 equals n plus m is equals to 1 because on this side L has a power 1, on this side L has a power n plus m, so this is equals to 1, and t on here has t raised to the power 2, here he has raised to the power m power, so your m will be equals to 2. Okay, so just you got the value of this constant m, and when you're going to plug in this m value in this equation, you can find the value of the constant n also. Okay, so now you got these two constants, n is equals to -1, m equals to 2. Now just plug in these values in your original equation, that is acceleration is equals to k, r raised to the power -1 and v raised to the power 2, right? So acceleration is equals to k v squared divided by r, that is the actual relation for this acceleration. And the conversion of units. So any quantity can be measured in several different units. For example, you can measure the length in miles, meter, inches, feet, kilometers, right? But you just need to know about the conversion between these units, how you're going to convert these units. Okay, so we'll do some conversion factors also. So suppose we wish to convert 15 inches to centimeters. Then you should know how many centimeters are there in 1 inch. So 15 inch is equals to 15 inch multiplied by 2.54 centimeter divided by 1 inch, because there is 1 inch is definitely defined exactly as 2.54 centimeter. So you will get 38.1 centimeter. Since you're going to get this inch cancelled by this, so you are left with the unit only centimeters. So your 15 centimeter is equals to 38.1 centimeter. 15 inch is equals to 38.1 centimeter. Okay, so the remaining unit is the centimeter, and that is our desired results. So guys, this is all about the units and dimensions, and we have all this table for the conversion factor. So you have these various units all for the length, different units for the measurement of length, different units for measuring the mass, different units for measuring the time, and these are the conversion factors as well for this. Okay, so we'll just do some problems as well. So suppose you have a question to convert 55 kilometer per hour to meter per second, right? So your equation, so you have in this question you have 55 kilometer divided by r, and you need to convert this kilometer, to meter and this r to second. Okay, so what we will do for this, we will multiply. So we will have 1 kilometer here. So how many, and since we need to convert this kilometer to meter, so we have how many meters we have in 1 kilometer. So we have 1, 2, and 3. 1000 meter in 1 kilometer, right? And then we also need to convert this 1 hour to seconds. So 1 hour we have 3600 seconds, right? So now this kilometer will get cancelled out with this hour will get cancelled out with this, and we have the units meter per second. So how you're gonna go convert this, you have 55 multiplied by 1000 divided by 3600, and I have, I guess, 15.28 meters per second conversion. Okay, so your 55 kilometer per hour is equals to 15.28 meters per second. Okay, so make sure this is the easiest method to do the conversion. Like, make sure you cancel out your units and you're left with the your desired units. Okay, now let's do this question. Which of the following quantities has the same dimensions as the kinetic energy? Okay, so your kinetic energy formula is this: half of mv square. So this is your half of mv square. So if we check this equation, this is your small m is your mass, right? So you will have capital M for this. Your velocity is L over T. So you will have square for this. So your equation is ml2 T minus 2. So this is the dimension for the kinetic energy. Now you need to check that out of these following quantities, which one has the same unit, same dimensions as this ml2t minus 2. Okay, so you can just do the calculations. If I go with the first one, this is ma, mass and acceleration. So ma means my m lt minus 2, right? So this is not the answer. mvx for the b part, mvx, m, v means L over T, x will have L, So this means ML2T minus 1. So this is again not the answer. C part, C means MVT. So I have capital M for mass, velocity, L over T, small t, this T. So this dimension is M and L. So this is again not the answer. Now my D part is MGH. So capital M for this, G is L t raised to the power 2. Then I have h. H is height. I'm going to measure it in L. So I have the dimensions ml2t minus 2. And I guess that is the same as the dimension of the kinetic energy. So this is your answer for this question. Okay, now let us check this E part also. So E is your mgt. So you have m, g is again your acceleration. Sorry. So t, and you have t. So t is again you have t here. So when you're gonna cancel it with this, so you have for this mlt minus 1. So this is again not your answer. So your answer that which have the same dimension as kinetic energy is just this D part mgh. Okay, and the next question is, which quantity with the same units as force times time with the dimension mlt minus 1? Okay, so now let us check this A part. A part is mv. Mv means mass into velocity. So you're going to take m, capital M for mass, and velocity is L over t. So you get mlt minus 1. Oh, that is the answer. Okay, so this is your answer. Now let's check the other parts. So now let's check this B part, mvr. So v is velocity, r is again length. So you have ml2t minus 1. So that is not the answer. C part, we have m v square. So L over t raised to the power 2 and L. So that means this has ml3t minus 1. That is again not the answer. Ma. So your mass and acceleration is L over t raised to the power 2. That means mlt minus 2. So that is again not the answer. And E part we have mv square over r. So you have capital M for m, v, L over t, square of that, and divided by one more L. So for this you will get m. This will get cancelled out with this. So you have mlt minus 1. Oh, v square L square ml t minus 2, sorry. This is t minus because L also has the same power, right? So mlt minus 2. So that's again not the answer. So we have the answer in this question, the A part, mv. Okay, the last question for this, the equation for the change of position of a train starting at x equals to 0 meter is given by x equals to half of at square plus bt cube. And the dimension of the BR. Okay, so now remember, whenever you have this type of equation, you have on left hand side you have only x, on right hand side you have two different parts, half of at square and then you have bt cube. Okay, so if I put the dimensions for x, I will have the dimension L. At square, well, here you will have a, and t square will be this plus b, and this will be with the t cube. Okay, so the dimensions for the b. So from this equation, if I say this should have dimension equals to this, and then this also should have dimension equals to this. Okay, so the dimension for, sorry, let me just take this. So dimension for A will be LT minus 2, and the dimension for B will be LT minus 3. Okay, so B, you're going to equate this thing to this, so you will get B equals to LT raised to the power negative 3. And when you're going to equate this thing to this, your A will be LT minus 2. So this is how we find the dimensions for different quantities in this.